Doc with another review here, Chapter M, Aberrations. Now, the word aberrations implies something that's out of the ordinary or something that's wrong or something that's bad. Well, that's because it's something nature does we just happen not to like. When you want to take pictures, we do not like the idea here of the red not bending as much as the blue and the colors spread out. That's called chromatic aberration. It's not really technically an aberration of nature because nature is perfect in the laws of physics. However, blue bending more than red does give us a slight blur in making photographs. Now, this is exaggerated here. So the white light that comes in, the violet end bends more than the red end, and all the other colors are in between. I simply use blue for the short wavelength end and red for the long wavelength end. Now, when you have the diverging lens, blue still bends more, but it bends upwards, say diverging, and red bends less. And you can see that the red focal length, if you have an observer looking back here, it appears that the light came from focal point red, and the blue appeared to come from focal point blue. And here, this is focal point blue, focal point red. If you had another ray down here, blue would come up here, and the blue rays would meet there. So the blue focal length is shorter than the red focal length because the index of refraction for the colors are slightly different. This is somewhat exaggerated. This is called dispersion. Dispersion is the spread out of colors due to the different wavelengths having different indices of refraction. Now, you can consider this as a sharp point for blue and a fuzzy point for red, because the red doesn't go there, and here a sharp point for red and a fuzzy point for blue. So we call these circles of confusion, and the best is a compromise someplace in the middle. You should put the screen to get the best effect. Let's look at another kind of aberration called spherical aberration, and here the marginal rays bend more than the rays near the center, hitting the center of the lens. The margins are up here near the edges, and this ray bends more, say these rays bend more than the rays hitting the center. This is exaggerated, but this does show the circles of confusion very, very easily. In this case, you have a sharp focus for the marginal rays here, and a sharp focus for the inner rays over there. But this is the best bet where the circle of confusion is the least circle of confusion. Well, that is another problem that we have to deal with cameras and optical applications. Here we have a third kind called the off-axis aberrations, and here these are blurs that occur for points away from the axis. So if I have a point up here off the axis, this is the optical axis, or the optic axis here through the center of the lens. That point will have an image that's a little bit blurry, like having a little tail, a little flare, a little comma, all right, like a comet. So this point is not imaged as a point. This is a problem in trying to get good pictures. Coma. Curvature field is another off-axis aberration where the points off the axis are imaged in a curved pattern here. Different places along the image are not going to be all in a flat plane. I remember going to a real nice theater in Philadelphia, and the screen was curved so that they could minimize this kind of aberration, the curvature of field. Astigmatism is another off-axis aberration, and for astigmatism, the point that is at the top, say this is the top, say I'm standing up here, and this is my head. If you look down from the ceiling, this is the top of my head. You look from the side, you would see me standing, and I would be up there. Now, when you look at the rays coming from my head, side view, these rays, these fan out differently. These are like vertical, and if you look from above, these would be like a horizontal fanning out. Bad news. They do not go to the same point. Point's a little bit different distance away on the other side. That's going to blur things. And finally, we have distortion. In cameras, we do need to have an aperture control, and when we have an aperture control, if we put the aperture here before the lens, a grid which really should be turned facing the lens, but I'm having it facing you so you can see the pattern. You would see on the screen, once again, this would face the lens, but for purpose of illustration, I have it facing you. This is shaped like a little barrel. This is called barrel distortion. If you put the stop, this is called the stop because it stops some of the light, but the aperture in the middle there, called the stop, or an aperture, the opening, this causes a distortion that's called pincushion distortion. Engineers can solve a problem here by putting the stop in between the two lenses, and these will cancel. Thus, in a camera, the lens that you actually will find is one made of more than one piece of glass. You do have a situation where you have the chromatic aberration. They have a doublet. They put a diverging lens here behind this lens, so the diverging lens helps to push things back. So you have a doublet, you have then these two sets of lenses here on either side, and you can get up to like 6 pieces easily for a camera lens. And the net focal length would be the focal length of the combination. Now here we have light going through the prism, and as light goes through the prism, blue bends more than red bends less. I had a German physicist once tell me that he remembered red bends less because the E sound, red bends less, the E sounds were the same, which he took note of because English was hard for him. So here we have the different indices of refraction for violet, say, to red. And for glass, we did say the index of refraction is 1.5. But you see here, it's a little bit different for the different colors, the different wavelengths. Diamond, we said, was 2.4, but you can see here it's a little bit different. The range here, when you have $1, and if it ranged a penny, we'd say it's 1%. And this is like $1.50, and it's kind of like a penny and a half. The range is a little bit like 1% roughly you're seeing here. If you look at the diamond, like $2.45, $2.41, that's like $4 cents on $2 is 2%, roughly 2% variation. So the diamond has a variation of 2% in the index of refraction, and that means more dispersion, and that's desirable. Now see, we're fickle. We said that chromatic aberration was an aberration, but now when it comes to diamond rings, we like it. We like the 2%, and the glass has 1%. So the high index of refraction of diamond and the higher percentage for the dispersion makes it for a good aesthetic ring. Well, we have a phenomenon here that's very delightful. The light, when it enters things like calcite, for example, an example of a birefringent material, you find that the polarization of light in the vertical and horizontal direction, in two different directions, they travel at different speeds in the material, and therefore they bend to different amounts. And since there's two basic types of polarization, you'll get like 2 rays, and you get double vision. Very, very nice, called double refraction. And this is the time when polarization was discovered. Say, this is Bartholon here making this observation. He was very much charmed by this effect, and many, many folks, which are just lovely to look at. So here, if you take a polarizer and have this, you have this double vision. Like, in other words, what's happening here is you put the book underneath the crystal, and then the light comes from the book up to us, and because of the double refraction, you get double vision. And if you take the polarizer and rotate it, you can get one killed and see just one instead of the other, and that demonstrates that's a polarization effect. So the ordinary ray would be the ray that you get if you simply have one refraction, like usually is the case. That's called the ordinary ray, and then because of the double vision, this is called the extraordinary ray. And when a polarizer is placed over it, you can rotate it and get one of the images or the other in terms of the double vision. You see one or the other based on the rotation of the polarizer. Now, this is another neat effect, polarization by reflection. Now, when light has mixed polarization, I describe that by having a little line going up and down, like a vertical polarization. The electric field is oscillating this way as the wave travels down. And the little dot means it's into the page and out of the page. So I have two polarization states, a vertical one, and then we can call the dot a horizontal one, where it's coming at you and going toward you. Now, when you hit the glass at an angle like 56 degrees, what happens is the refracted angle bends toward the normal, and the reflected angle is such that the angle of reflection is the same as the angle of incidence, 56 degrees. Now, when this is 90 degrees, the refracted angle makes, the refracted angle is actually this angle in here, but if you look at the angle between the refracted ray and the reflected ray is 90, then what happens here is that you cannot get these this polarization that's wiggling like that. You can't get that going to your eye because that would be longitudinal. You can never wiggle toward your eye and away from your eye. That's a longitudinal wave. Now, sound does that, but not light. So therefore, this one is killed, and only the dot can go to your eye because the dot is in and out of the page, and that is perpendicular to the direction of the travel of the wave. So that's polarization by reflection, and this kind of glare that can happen with polarization is polarized with this reflection, and you can get a polarizer in your camera and like kill it so that you do not get that reflection from reaching your camera and messing up your picture. Finally, let's see, we have a couple more things here. We have the liquid crystal display, which is very, very neat application of laws of physics. You have this property of these liquid crystals, which I like to think of as baby French fries, that you can put them between two plates like a sandwich, and if you twist the plates, then you twist the crystals. So the crystals here, one direction, say they're vertical here, and then by the time you get here, they're horizontal. And what they do is they take polarized light. Here I have a polarizer, so the incident light becomes polarized in the vertical direction. They will twist the polarization so that it comes out horizontally polarized because of the twisted effect with the crystals. Very nice. So you get transmitted light. This is bright. Now, what's really neat about these crystals, if you zap them with electricity, you apply electric field, they all straighten out. And when they straighten out, they don't rotate the polarization. So the polarization goes through unaffected. And now, since this polarizer is crisscrossed, you get dark. See, this polarizer was turned 90 degrees so that when this rotates 90 degrees, it can slip through. But now, since there's no rotation going on due to the liquid crystals, the vertically polarized light goes straight through, but then gets killed because this is only allowing the horizontal to get through, so it's dark. And in this way, you can control with very, very little energy and electricity, you can control little rectangles and make numbers on a watch, and that's the liquid crystal display, and also the principle in the computer monitor that uses liquid crystals, and then it's a color. The one has the 3 pixels of color, which we'll talk about another time. So here, that's a very, very neat effect. The properties of liquid crystals are electrical in nature. When you apply electric field, they straighten out. They're mechanical in nature because if you twist them, they'll then twist from being vertical to horizontal, and they also have optical properties where they rotate the polarization of light when they're twisted in this fashion. If they're not twisted and they're straight, they do nothing to the light. The light just simply goes through. Finally, we have an example, a beautiful example of polarization in art, and this is Austin Wood Camero. And she looks at birefringent material, like Scotch tape has that, little potato chip wrappers will have that. And these are very, very neat things. They basically will take light, and different colors of light will be affected by the birefringent material, like cellulose, mica, stressed plastic, sugar solutions, for example. And when you have a polarizer on one side, they'll play with the polarization depending on the color, the wavelength of light, and different rotations will occur, and you can control the color by thicknesses and by cutting the little birefringent pieces, the birefringent pieces that are going to be placed on top of the polarizer. She has Polaroid glasses so she can work with it, and then she gets color when no color is really there. There's no pigment, no traditional color pigment. It's all polarization. So the color, I say, is not there. I mean, traditionally it's not there. You're not using paints, you're not using colored pencils, which you would normally use to get a colored effect. This is basically all clear. And in fact, if you don't have the glasses on or don't have a polarizer, now she has a polarizer in front there, you will not see the effect. So she can make wonderful pieces of art this way. And here, there's this neat little animation which shows you that the polarizer in the front, when it rotates, it changes the colors so that when it goes 90 degrees, you get the complement. So like yellow becomes blue, blue becomes yellow, green becomes magenta, and very, very nice effect. So this is an example of polarization in art, and that concludes our discussion of Chapter M.